I'm going to narrate a lot of this session for you. What we're going to do is we're going to do a couple of concrete experiments, concrete in its two natural states, and we're going to we'll give you an opportunity to take recordings, take readings. Now my understanding is that, are ye all doing the leaving, sir? Okay. And my understanding is that there is a chance that some of you are going to record some of this and report on it for your leaving cert by way of experiment, possibly. It can be, so you may. So what I would recommend is I have a meter stick here, and you know what the consequences of setting out the line are with a meter stick. Actually, as it happens, this is only a pointing device because I can't find anything else. Now, we're going to be looking at concrete in two states. Are you familiar with concrete or some of the concrete expressions, like for example, workability, consistence, slump test, flow table test, concrete design, concrete mix specification? Okay, I wouldn't expect that you would be, as it happens, but my understanding is that you may be required to write up one or two of these experiments as part of your portfolio. I would suggest that if you take some of the readings here and by way of proof, your photographs, etc., that you've done the tests, even if you want to get some of your friends or whatever to record you in the photographs, then I would suggest that, I don't want to make it sound very simple, but I would suggest that these would be relatively straightforward experiments to write up. But as experiments are written, make sure you do it in accordance with good practice and so on. So what we'll be able to do is give you a full rundown on the rig, a full rundown on the procedure, and we'll have a quick discussion on some of the happenings and findings that occurs in our experiments here, right? Now, just to start the ball rolling, I think everybody knows that concrete is a fairly predominant construction material, construction/engineering material, yeah? Now, can anybody give me a reason why it's an unusual engineering material? You mightn't get it off the top of your head. I do put the questions out just because you might know, but it's an unusual material from the point of view. Here's the makings of concrete. Look, very, very straightforward. An aggregate. This one is coarse, an aggregate, a fine one, looks like sand, and having said that, these are all graded. And a cement. This cement, as it happens, we don't have any silo facilities or anything here. This cement is out of the bags as you know them, and then we have free water. Now, you've all got a handout, and on the back of that handout we have produced a mixed design, right? Now, the mixed design is designed specifically to suit these three tests that we're going to carry out today. Brendan and Owen are going to conduct the tests, and I will do my best, as I said earlier, to keep up with them and narrate our way through these tests as it goes. If you have a pen, if you record it, or if you want any further information at a later stage, we can furnish that to you, okay? Now, we have designed a mix there, nothing for you to worry unduly about, but if you notice at the top of it, or up near the top, you see that it's a design mix to have a strength of 30 newtons per square millimetre. That's the compressive strength by design, and we've designed it to have a slump. You're familiar with the expression, the term slump? Okay? It's designed to have a slump that ranges somewhere between, or should fall somewhere between 30 and 60 millimetres. Okay? That is the plan. So we have that concrete mixed here, and we're going to do the test to see, number one, does it slump as we designed it, and number two, and if it doesn't, we'll try and come up with a few ideas as to why it didn't or how we could make it, and number two, does it attain the strength that we set out and designed it to have, right? Now, just by way of a bit of information, one of the reasons we need to know, or we specify a slump, is on site. Has anyone any experience of being on site and a concrete lorry arrives and pours out X amount of cubic metres of concrete? Yeah? No? Maybe not. But on site contractors who do a lot of concreting work will have a lot of equipment fit to handle a particular type of concrete. For example, some contractors will have vibrators, pokers, formwork, etc., and they'll be fit to handle slightly drier concrete than others, okay? There's a leaning in the industry towards more pourable concrete, self-leveling type or self-compacting type mixes, etc. So there's more and more tests coming on stream with regard to the various different types of concrete. However, for example, if the engineer says that for a particular beam, column, foundation or whatever, the concrete needs to be 30 Newton in strength, that's crushing strength, okay? And the contractor says, when you're delivering the concrete to us, we can handle concrete with a slump of 30 to 60 millimeters. You design for that, strength-wise to satisfy engineers, workability-wise to satisfy those who are going to handle the concrete, and you're going to see here the essential difference between a very workable concrete and a concrete which would have technically the same strength but not as workable. Okay, so you're going to see that here with a slight difference in the mix between one and the other test. Now, we have a batch made, and all of this, and this is in the concrete that we have made here, and this amount of water. This is the full amount of water required by our mix design, and the reason we need this full amount of water, this is called the free water cement. We have, in laboratory conditions, we have what we could classify as extremely dry samples. On site, in the concrete producers, factories, etc., or plants, they don't have aggregates like this to work with. They have stockpiles, but a lot of them are subject to the elements. It rained last night, so this, and this is going to be wet. So if we need this amount of water, according to our design mix, and this is wet, what do you think we need to do with this? Reduce it somewhat. Okay. So in the plant, things are slightly different to here. We use free water and we use completely dry aggregates for the most part. In the plant, this morning, up in Banagher Concrete, Larrigan Quarries, wherever you go, there's somebody some technician, in the lab, going out and carrying out tests on these to see what the moisture content is, get the volume of it, and take that amount of moisture away from this to give you exactly the same mix. Okay, that's pretty understandable and straightforward. However, just to recap, the concrete we have is all of that, that, and that mixed together here. We're going to do the slump test first, and then we're going to look at the crushing of a cube. So we're going to look at two tests for concrete in its fresh state, and we're going to look at one test for concrete in its hardened state, okay? Now, just before, so as we don't have to come back to this, these are the type of failures we're going to be potentially getting when we crush our cubes. That's the hardened state. We look at the fresh state now quickly, and when we manufactured the cubes, we had no choice, and it's something I want you to bear in mind before we get down to the compression machine. In order to be ready for this session, and because we have students doing projects here and using up our curing tanks and baths, we had no choice. We got 21 days to make the samples for this. Has anybody any idea what age concrete should be before its strength is tested? Have you heard of the 28-day strength? Some of you may or may not. However, what we do, just briefly, we've manufactured 100mm cubes for our experiment here today. The reason we manufacture 100mm cubes is in accordance with the codes of practice, if the maximum aggregate size is 10mm, we use 100mm cubes. If we were to use larger aggregates, for example 20mm, the codes require that we go up and start using 150mm cubes. The essential difference is it's a bigger area, it's going to take a bigger load to crush it, but if you divide that load by the area, or a smaller load by this area, you should theoretically get the same strength, or thereabouts, yeah? So that's why we're using 100. Just in case anyone is going to report on a cube test, the way we manufacture this is, we'll fill our concrete into the cube, we have to compact it as best we can. The standard is a 20mm square tamping rod, fill it in 2 equal layers, and 25 tamps for each layer. Then you trowel it off. The alternative is, and the way these cubes that we're going to use today were manufactured, we made these cubes, we filled the molds, and we have a vibrating table outside, which is the same effect. Both methods, as long as they're carried out in accordance with the codes of practice, are acceptable for manufacturing cubes. Okay? You can also use Popper vibrators that are, if any of you might have seen them, they're connected to compressors, you insert them into the concrete and they vibrate it. That would be very typical of the way concrete is vibrated and compacted on site for about 99% of the time. Okay? So that would be the manufacture of the cubes, and then after somewhere between 16 and 72 hours, the cubes have to be struck, which is essentially take these molds off them, placed into the curing tank, so as the chemical reactions between the cement, the water and the aggregates can occur in the proper and appropriate conditions, which is that the moisture doesn't evaporate or leave the mix too quick. So that's why the European codes require that these samples are placed in a curing tank for 28 days, and the temperature of the water in the tank should be, according to the code, 20 degrees plus or minus 1 degree. So a range 19 to 21 degrees for 28 days. Take them out, dry them, clean off any rough edges, projections, and test them. Okay? So that's the hard state. So that's the last experiment or test we're going to do the demo for today. First of all, we're going to do a demo. We're going to test the workability of this concrete sample that we have designed to be a slump of 30 to 60 mil. So hopefully this is going to slump 30 to 60 mil. Just before you come and gather around this experiment, and bear in mind that the session has been recorded, so just the cameras make space for them. Before we start this, just bear in mind that all of the equipment, which I'll quickly run through with you, all of this equipment must be dampened and cleaned before use, and cleaned afterwards, of course, which is standard laboratory stuff. But if you're in practice, if you're out there in the field in practice, it's imperative that all of this procedure is carried out strictly in accordance with the standards. The standard for this test, the slump test, is ISEN 12350 Part 2. That's the slump test. Now that may or may not be relevant to you, but just in case any of you wants to do a little bit of further reading or a little bit of research, if you decide to do the slump test as one of your experiments for your leave insert write-ups. Everything here has been dampened. Before you come around here, if you want to just come a bit closer to this and have a look, we'll be doing the two tests in this spot. So you can just form a circle here. And the lads are going to conduct the test here, because they've got better boots than me. And I just narrate as best I can for you, okay? If you've got any questions, don't hesitate to ask. Now, what we have to carry out the test, this test is on the face of it, not very technical on the face of it, and it's relatively simple. The apparatus is a truncated cone. This will actually form a true cone if it were extended. This is truncated here, 200 millimeter diameter, 100 millimeter diameter and 300 millimeters high. That's the standard cone, okay? This little funnel is just an assister to fill the cone, just to save on the mess and speed things up a little bit. The tray is pretty much standard in any of the laboratories. It may or may not be. It may be on an extremely smooth, hard surface in some other labs or in concrete plants, okay? Now, what you have here is this is a standard, it looks like a bar, which it is, and it's a standard bar, which it is. It's got, according to the code, to standardise it, it's a 16 millimeter diameter bar with a hemispherical end on it. Half a sphere, okay? Now, the code requires to carry out this test, fill the cone in approximately 3 equal layers, depth-wise. Each layer gets 25 vertical clamps of this rod, not 24, not 26. In order for unification and standardization, it must be 25 layers, otherwise the test result is not valid. Fill it in 2 layers. The code says don't let the tamping rod touch the tray when tamping the first layer. When tamping the second and subsequent layers, the tamping rod should penetrate the previous layer a minimum of 25 millimeters on each prod. Okay? So 25 vertical prods for each layer. When the third layer is tamped and filled, it's going to be trowelled off level on top. Any excess concrete is going to be removed from around the edge off the tray. It's going to be just brushed down or sponged down, and the mould is then going to be removed. The code says when the mould is filled and trowelled level, this mould should be lifted within a 30-second period. When you start lifting, this is why on the face of it, it seems very simple. There are some rules and regulations in accordance with the standards and code, so that if we're doing a concrete test here, and you're doing a concrete test in Roscommon, and someone else is doing one in Spain or anywhere across Europe where the Euro codes are standard, they will do a slump test exactly the same as this, so as the results are standardized. Okay? So you've got the level of the top surface, and the code says remove the cone within 30 seconds. When you start lifting the cone should be lifted within 10 seconds. That's in the code as well. So that's going to happen a little bit inside the 30 seconds here for obvious reasons. This is always generally much easier to conduct and carry out under laboratory conditions. Okay. Now, we have a shear failure here. That is not good, as it happens. However, the slump test is valid for slumps ranging from 5 to 210 millimeters. So we'll see what happens here. If this is greater than 210 millimeters, we might just conduct it again. Now, what you're going to do is the slump is measured from the bottom of the rod. A little bit of judgment involved because it's not absolutely an exact science. If you think about it logically, it's not an exact science because we've designed the mix to be a slump somewhere in the range of 30 to 60 mil, which is way exceeded here. We can assume there's a problem here, okay? There's a problem here with this mix. Now, what's the slump, Owen?
170.
The slump for this is 170 millimeters, okay? So you record that. Now, can anybody suggest why you think that might have slumped too much? But I do want to say, by the way, folks, that is not by design. We didn't want that to go like that, so as we could ask you this question. But can anybody do a little bit of thinking and say, or how could you have kept that standing up a little bit better?
Cement to water ratio, is it?
Water-cement ratio, yeah. So more or less water, do you think?
Less.
Obviously. Less water, possibly more cement, which is going to start making... Now, can you imagine a lorry load of this? More cement is going to make this very expensive. It probably increased the strength unduly over and above. It could affect curing times, etc., etc. The bottom line is it wouldn't comply. It's quite possible, and this would be pretty standard, where moisture readings are not being taken correctly and adjustments for free water cement ratio are not being made correctly. This would be your standard, this would be very standard in concrete plants. And it would be, my opinion in a concrete plant that this happens is the moisture readings weren't carefully taken or adjusted correctly. Okay? So yes, it's very likely in this particular scenario that there's too much water in this. However, the slump test is valid. It doesn't comply. The contractor says he wants 30 to 60 millimeter slump. He might just say, I don't want that concrete. Okay? There may have to be adjustments made to it. But it's very difficult. I have to say most manufacturing plants, it may happen in the lab, in samples, but it won't leave the plant. Generally speaking, they will deliver the product as ordered, okay? So this concrete was supposed to have a crushing strength in 28 days' time of 30 newtons, and it was supposed to have a slump somewhere between 30 and 60, and has exceeded it. It's absolutely certain that it's a water issue here, guaranteed. So if any of you is writing up this experiment, the slump was supposed to be 30 to 60 mil. It recorded at 170 for any of you who's recording it, and we have kind of discussed the conclusions. So if you're going to write up this experiment for your leave insert, there's some results. Take the photographs if you haven't already done so. There's the slump as it is, and you can do a little bit of background research as you want, and you may be able to come up with some other conclusions. But if you quote what we're kind of after saying there will happen in the lab and in practice, I would imagine you should be okay. Alright?
Lads, anyone get a photograph of that?
So if you want to just get a
Go for your
photograph
chef,
on this bit
step
measure, newtons with a slump of 60 mil. Yeah? Also, the code allows concrete to be specified with a strength and a flow class. Okay? Now, this test here would be more geared and leans more heavily towards more flowable concretes and self-compacting type mixes. Okay? In the codes, you've got 6 classifications, 6 flow classes, F1 to F6, which I would recommend that you look up. There's no point in me quoting figures and quoting bands here. But what we're going to do is we're going to do a flow table test on this sample. We're going to calculate very, very simply. You'll be amazed. Even I can do it. You'll be amazed how simple these tests are on the face of it. But there is a technical reason behind all of this. The reason all of these are standard is so as no matter where these tests are carried out across Europe, everyone does the same thing, and then the readings are standard and the results. Okay? So if you want concrete and you test it, this is the way you do it. If you're making concrete and you test it, this is the way you do it. So everyone is speaking or singing off the one hymn sheet. The apparatus here is a shorter but very similar truncated cone, 200 millimeters at the bottom, 130 millimeter diameter at the top, and 200 millimeters high. Again, an assistant to fill it, an aid, just a funnel, may not be needed. And this is the clamping rod in this particular case. A square, 35 millimeter square clamping bar, the timber one in this case. Fill the mould, in this case, in 2 approximately, you don't measure, but approximately 2 equal layers. Each layer in this particular case gets a very light tamp with this rod 10 times. 10 of these, very light, just to flatten down, and we'll put the next layer on top of it. Okay? This table, yeah, we'll see in a minute, is designed to be either fixed or held here. If you were doing this outside of the laboratory, we're very confident and happy that our floor here is perfectly level. The code requires to carry out and conduct the flow table test. This table must be placed on a perfectly level surface or alternatively level it. So, because we're confident we didn't, but if you're reporting this one, make sure you report that this table, on which we're doing the test, should be perfectly level. How you will gauge that is use the spirit level in 2 mutually perpendicular directions, and if both of them are level, it's perfectly level. Okay? Now, after it has been leveled off, the code says 30 seconds to remove the cone. Okay? Now, what we're going to do is, the table is so designed, there's a design travel on this table. There's a handle here. It's manual, fortunately or unfortunately as the case may be. What's going to happen here is this part of the table can lift 40 plus or minus 1 millimeter. It's going to be lifted by Owen 15 times and basically let drop. So he's going to do it so he's noisy, so I'll let him do it 15 times and take it from there. Okay, that's 15 times. Now, the flow classifications that we mentioned, there's 6 of them, F1 to F6, they're as simple as, take the widest spread of the concrete flow, take the widest spread, in two mutually perpendicular directions. The easiest ones to do are, obviously, parallel to the sides of the table. So the maximum flow spread, for the two tables,
590, 560.
590 millimeters and 560 millimeters, okay? The flow classification for this mix, based on that test, is the average of those two readings. So it's 590 plus 560 divided by 2, which is obviously 575, okay? So the flow classification here, or the flow measurement, is 575 mil. When you get a chance, if you note that, or mentally note it, look up what the 6 flow classifications are. You'll see that each classification has a bandwidth in millimeters. And see which of those classifications does 575 millimeters fit into. And that's the flow class for that concrete. Okay? So we'll just say, for example, I won't give you the figures because I think you should go and do a little bit of independent research on this. If, for example, flow class F4, what did we say the reading was? 575?
575.
575. Just say F4, flow class 4, is 500 to 600 millimeters. Well, that's where it fits. So this is class F4 concrete. Is that okay? Just a few things to note on this, right? There's obviously, the more that flows, would you agree? The more that flows, the easier it would be to handle it and pour it and compact it. If that was to stay standing in the cone shape, it would be actually difficult to handle, difficult to shovel, etc., etc. Okay, so obviously, the more it spreads, the bigger the classification is going to be in millimeters. Okay? If the last classification that exists, that concrete would have flowed over the table. So just say, for example, it was lifted 15 times. If that concrete had flowed over the edges of the table after 10 lifts, the test is over, and the concrete is classified as the last one. Okay, it falls into the last category. The last category is, if when you look up the categories, F6 is going to be greater than, and greater than is the dimensions of that table. Alright? So if it was to flow over the edges, you stop. It's over. The test is over. Otherwise, it's 15 times. The reason it's 15 times, it's not 14, it's not 16, it's 15 lift and drops, because somebody could be doing a test like this in another lab and they'll do the exact same thing as we did. And then our results are unified and our results are standard. Okay? So the reason, on the face of it, these are physically very simple tests. They're technically a little bit more difficult than they appear on the face of it. And the key overarching factor here is that they're standard. Nobody will ever do a flow table test in Europe differently to that, or they shouldn't. But they might do it better than that, maybe, but certainly no different. And some mixes will flow off the table, some will go like that, and some will just stay in the bin. Okay? A few things that the codes of practice. The code of practice for this one, by the way, is Irish Standard Euro Code 12350 Part 5, okay, for the flow table test. It's a measure of how workable and compactable the concrete is. A couple of things it tells you to look out for, and this mix is good from this point of view. You see the way these coarse aggregates have segregated here? Look, as the fellow says, they're out on their own. Yeah? They're kind of separated from the concrete as we know it. You're required, when you're doing the flow table test, to note this and give an approximation of how much of this is going on. This would probably be classified as being okay. However, there may be a chance with this mix. As I once said earlier, it's a harsh mix. It's very visible as the coarse aggregate. There's a chance that in the transportation, the lorries, the pouring, sometimes when concrete goes on site, it gets pumped. This concrete would be a candidate for when it's been pumped through tubes or whatever, the aggregates are going to segregate like this. Can you imagine pouring concrete into a mould to get a beam or a column or maybe a floor and take all your formwork off and end up seeing this type of a surface on it, where segregation has occurred and you won't achieve your nice smooth concrete finish as desired and so on. It would be classified in concrete terms as a disaster as it happens. So you would want to note this. Now, to get a little bit more in depth into it, you'd want to be gauging how much of this is going on, etc. Nothing for you to worry about. But when you get involved in a concrete lab, you'll be looking more in depth at this type of thing. But just to note, when you're finished at slump test, the code requires check this and see is there a little bit of segregation liable. May or may not be a problem. The more of this that goes on, the greater the likelihood is that it's going to separate on site. Also, the code requires look around the edge. It's not the case in this particular mix. Look around the edge for a very fine, thin ring of a cement paste on its own. And that would signify that there's potential for this mix to bleed. It's called bleeding of the concrete. Again, it will have all sorts of implications on pouring, handling, and particularly concrete finishes. Okay? Most concrete is left, shall we say, in a naked condition. It may get coats of emulsion paint, it may get a little bit of fireproofing, but most concrete is fireproof by virtue of its design, reinforced concrete, cover to steel, grades of concrete. It is fireproof in itself, and it merely gets a little bit of decoration. For the most part, reinforced concrete work is left exposed. So finishes, bleeding, segregation, all of that, those possibilities are critical to the finishes that we can achieve with our concrete. Okay? So that's the last of that. I won't harp on too much more about it. That's the test for consistency or workability, as you might know it. It's the second one. So generally speaking, concrete is going to be specified with a strength and a slump, or a strength and a float class. Okay? And that's the test for the float class. Now, if any of you decide to write up these experiments, right? We have a company here that supplies materials to the lab called Sika. Some of you might be familiar with it. If you look at the yellow poster, you get the name. Just as a by the way, I have looked up some information on this. Sika have produced some very good 10-minute long videos of these experiments having been carried out in exactly the same detail as this. If you need any recap on this, if you go on YouTube and just type in flow table test and look for the one, it's actually, the name under the video is Sika Limited 1. And you'll see this test being carried out again in its entirety in exactly the same way as this. Okay? Just by, in case, some of you may find yourself writing up some of these, hopefully not at the last minute, but, okay? So that's the end of the concrete in its fresh state. Now we're going to look at the sample that we made for you 21 days ago. On the handout you've got, right, we made a cube. We only need one cube for the demo. On the handout you've got, there's a section for this compression test. Part of it is a little table to fill out the data, but we're not going to really go there because it would take about 20 minutes in itself to do that, and we just don't have that type of time facility. But basically what we're doing here is, we're going to crush the cube in a compression machine down the lab, right? That cube, that compression machine, will not allow us to crush it unless we give it some critical information and data. The critical information is the dimensions of the cube. Just because we made a 100mm cube doesn't say it's exactly 100mm, okay? It may be more or less. We have the dimensions of that, which Owen will fix in. But for all intents and purposes, for the purpose of your report, I'm sure you will satisfy all your examiners if you say it was a 100mm cube. This machine here is called a Buoyancy Balance. Basically what this is going to throw out, we're not going to give you the figures for this because I don't think you need to go there. Any of you that's doing physics will touch on this. Anyone doing physics as a matter of interest? Archimedes principle and stuff like that, yeah? Okay, this is basically a play on that. This machine, with a little bit of rigor, it will give us the density of this. Bear in mind that we compacted this as best we could. That doesn't say there's not voids in there, etc., and you can't just take it. Laboratory practices don't allow you to take anything for granted. You've got to just work everything out and check. We're going to calculate for this, using this, Owen will have it done quickly. We're going to calculate the density of that concrete. We're going to calculate the the weight in air, weight in water, and the specific gravity. This machine down here won't allow the test to be carried out unless that data is inputted. So this would be an integral part of concrete cube crushing. However, due to time limitations, we're just going to feed this information in to the compression machine down here. But essentially, if you are recording it, this is called a buoyancy balance, and it's based on Archimedes' principle. Because we'll weigh it in air, we'll weigh it in water, we'll take the weight of the cage away. There's a little bit of manipulation of the readings. Relatively straightforward, but I don't think you need to worry about it. Just to be aware that we need it to conduct the test.
We also have the dimensions. The height, the width, the depth, where the width and the depth are crucial because that's what the forces want to bear over.
Absolutely. So, the practice is, take your sample, do all this business here with it, dry it off as best you can, and essentially crush it. Now this cube, as before Owen was aware with it, this cube was manufactured in the mould behind you, and you can see test cube T5 written on here. That was the exposed, that was the trowel surface, okay? We marked them. The code does not allow you to crush this cube with that face in contact with either of the two platens. And what we generally tell students, purely as a rule of thumb, the theory is don't have the platen on that face. But the easiest way to ensure that is mark that face when the concrete is fresh and have that face facing out through the window of the machine when you're testing it. And then it can't be between the plates, obviously. Okay? But just to be technical about it, the code requires that you don't have the plate in contact with that. So Owen is going to put this into the machine, input the bit of data that's required, just has to dry it off. Again, the practice and procedure is to dry it insofar it's going to remain damp. As it happens, when this concrete cube is crushed, you will see that the concrete is still immature. This concrete won't be white. This concrete is going to be nearly as dark inside as it is on the outside, having been wet. It's not fully dried out, and since the day that concrete was essentially born, it has been in a curing tank in water at 20 degrees, okay, for the last 21 days. So if you want to just gather around Owen down here at the crushing machine. Okay, now just while Owen is setting this up, just a few things to note about this, okay? We have a crushing machine which is actually set up. Again, there was no need for us to start doing all this here because we wouldn't have time. But this machine is actually set up to crush 100mm cubes, okay? Different parameters, but it's set at the moment to do 100mm cubes. When you get a chance later, if you're going to take photographs, you'll notice that the exposed face from the cube is facing outward, and Owen is just inputting the data here. Few critical things to note here. This is a 100mm cube. The cube depth in this particular case, for example, was 98mm, okay? So the code requires that you put in the true dimensions, not the assumed ones. We mold our cubes in 100mm molds. It doesn't say they're going to be exactly 100. The crushing of the cube is going to be crushed over a particular area, so it's absolutely critical that area. When you go back or when you're on the bus home, take a 100mm square cube and calculate the area of it in square millimeters. Some of you probably have it done in your heads, I'm sure. Okay, yeah. Now take a 99mm square cube and calculate the area in square millimeters, and you'll see the difference. What Owen is doing at the moment is one of the key drivers in the code of practice for carrying out this test is that the concrete at no stage gets any sort of shock loading. This concrete must be loaded at the moment the two platens are moving together and are possibly not in contact with the concrete just yet. Keep an ear out as best you can, there's a lot going on here. Keep an ear out, for this machine is going to slightly change its tune when the pressure starts getting applied at a constant rate. Owen is going to ensure, insofar as is reasonably possible, within plus or minus 5 kilonewtons per second, Owen is going to regulate the rate at which the load is applied to the cube. It must be a constant squeeze from the minute it's loaded. The rate at which the codes require the cube to be loaded is 6 newtons per square millimeter per second. Plus or minus 2. Okay?
Listen now.
Now, can you hear that slight change of tune there? Now the cube is in contact with the plates and it's been loaded at a constant rate. As we speak, and as I just said that, there's 73, 74 kilonewtons of load on the cube already, okay? So Owen is going to regulate this. Based on our previous experiences of yesterday and today, we're hoping that, now by the way, we're hoping upon hope, at 28 days this cube should have reached a crushing strength of 30 newtons per square millimetre. We're at 130, we're hoping this is going to go up over 250 or thereabouts at least, okay? This machine, when the concrete crushes and fails, it's not going to go back into a powder form. It's not crushing as you might imagine it. This cube is going to come back out of the machine just cracked. It probably will be all intact, but it will have failed. The machine will sense when that failure takes place. It will stop loading it, it will remain static for a few seconds, and it will give us the readings at failure. It will read out the maximum load at failure, and it will also give us the stress at failure, which should be that 30 newtons per square millimetre. So all we can do is just wait. It won't take too long. Another few seconds. So this test doesn't take long.
It's gone now.
The cube has now failed. The machine has stopped crushing it. It's recording it. It's working out the data that was inputted to it. And there we go. Now, for anyone that's recording this, the maximum load that was applied to the cube was 275.1 kilonewtons. Kilonewtons now, right? When you go back to school or on the bus or wherever, work out what magnitude of loading was that. 275 kilonewtons. Go back from, that's a weight, go back to a mass and work out. See, can you come up with an equivalent? What's that? How many articulated lorries was basically crushing that cube? You'll find quite a few. How many cars was basically sitting on that for the duration of the last 2 or 3 minutes? Quite a lot. You'd be surprised if you can work that back. Now, the sample stress, the failure stress here, at 28 days, if the cube was 28 days, we designed it to be 30. This is actually a very, very good. It had some failings up here, this type of concrete, in its fresh state. At 21 of the 28 days, this concrete has achieved a strength of 27.68 newtons per square millimetre. So that is well on its way to satisfying the requirements of the design. I would have absolutely no doubt, but that concrete was going to be 31 or 32 newtons per square millimetre. Okay? So what Owen is going to do now is we're going to just take back out the sample. You're going to see that it hasn't disintegrated. That's not the purpose of the exercise. It hasn't disintegrated. So what we'll do now is we'll have a look at it and see how much of it can we strip off and what sort of failure it is. And while Owen is just taking a little bit of that, I'll just get a sample or two here. Now, of course, if it were to crush completely down to absolutely nothing, it would have been a total disaster, okay? This is generally, if you can achieve your strengths and end up with a specimen that looks something like this here, this is generally what you're after, okay? You can probably see why, but this here would be lovingly referred to as an apple core failure. Can you see why? An apple core, yeah? Now, in case you're wondering, the black dots here are actually little an experiment students were carrying out where they replaced some of the porter aggregates in this mix with rubber crumbs. These are essentially old recycled tyres shredded up, and the rubber was used instead of some of the, we call it the stone or the coarser aggregate, okay? It was for experimental purposes. It had its pros and cons when tested. The students here for their project work would write reports and absolutely have to draw conclusions. If it was good, why? If it was bad, why? It's not just a matter of saying it looks good or it looks bad. Okay, so that's the type of failure. Now, I suppose in fairness you could nearly suggest that that is tending towards that shape. So it would be a good failure. When you're finished in the lab then, you'd have maybe a close look at the texture inside the failure. Can you see that the concrete is still relatively dark? By comparison with this, which is much more mature. In actual fact, this is probably a couple of months old now. This concrete, as you can see, you might be wondering, this was an experiment a student carried out, and there was a placement of some polymer fibres as well. And it was experimental work. See, what difference do they make? Do they make it stronger or weaker? What's the benefits? What's the pros and cons? Same with the rubber, etc. We have a couple of students this year putting in crushed glass into the concrete to see what benefits there are. And there's various other. For example, if you were a student here, you come in and say, I want to do a project. I like the concrete lab. I like that type of work. You could come in here and say, well, I know, I've read an article. I see where there's a particular material. They're having difficulty recycling it. Could we crush it up or could we use it in concrete? Let's do some tests. So you can come up with little projects like that. Or the lecturers would give you some projects like that. Because very often companies wonder, this is a byproduct of ours. Like, for example, furnace ash. This is a byproduct. We get it very hard to get rid of this. Could it be used in concrete? And if so, what would be the benefits or the pros and cons? You'd always look for example, aggregates. If you look at this disastrous one here, I can pass it around very quickly. But if you look at this one here, if you look closely, you'll see where the little holes remain where some of the aggregates have actually pulled away from the concrete and just left their own track behind. There's a classic example there. That is a classic example of bond failure. The bond between the concrete cement paste and the aggregate has failed there. Otherwise it wouldn't have separated. If you look again carefully and closely at this, somewhere, here's one here, here's an example. I don't know how well you can see it, but I can pass it around. The aggregate itself in this particular sample has cracked. Okay, so there's aggregate failure in here. There's an inadequate aggregate. Sometimes this surface texture, if it's too smooth, will affect the bond. Sometimes the bond can be affected by too much water, an inadequate cement paste, etc., etc. Okay? So there's many factors. So a lot of this, the tests for this, all of these tests here that we have conducted today, this is probably a little bit more technically challenging. There's a bit of work. Knowing how to use the machine, etc., etc., is not for everybody, only the experienced people that uses this. However, you probably will have noted that in general, the tests are relatively simple and straightforward. However, as engineers and as concrete practitioners, the big key aspect of doing concrete tests is experience. Anybody could put this in, pull the lever and crushed it. This would be a disastrous failure, by the way. This cube came out of this machine looking like this. There was no scraping required. So that's a disaster. But why is it a disaster? There's no point in coming and saying, oh, the concrete mix failed, it was a disaster. The next question is going to be, why? What caused this failure? How do you amend the mix? If someone said to you, how can we amend this mix so as it won't be a disaster? Different aggregate, different cement content, different paste, less water, more water. It's all experience. But you will find, when we were looking at the flow table, the slump, when we had the test completed, we again looked very carefully at the samples, and that's what we're at here. Now, just to finalise this and finish it off, the codes have a very rigorous procedure for recording all of this. Let's assume that this concrete here was brought into the lab, 28 days time it was tested, but it was taken out of the back of a lorry. And this concrete is a sample from concrete that was poured into a bridge abutment, or a bridge column. And now we have evidence that it's disastrous material. The bridge is still being built. In reality, what happens is this gets reported back from the accredited lab. Accredited, by the way, is someone who's worked to all their standards, get checked regularly, and companies use them to check all their products and stuff like that. Most of the concrete producers have their own accredited test labs now for ease of testing and so on. If that concrete is in a bridge somewhere, or a column or a beam, that has to come out. A disaster all around. Contractor, the engineers, meet up, has to come out. That beam this concrete in that beam, granted it's a steel one, but if this concrete in a beam over your head, or to be carrying floors, or this has to be removed again. So it is a disaster. I have to say, 99.9% of the time, no disastrous concrete leaves concrete manufacturing plants anymore, because they have their own accredited test labs and procedures. But if it did, there's no point in saying, we just say for example there's 10 bridges on the bypass and this concrete is in one of them. There's no point in coming along and saying, well, that concrete, we know it was on the Athlone bypass. But Jesus, which bridge is it in? Or where is it? So there's a very rigorous procedure for sampling and taking the samples, marking them, recording them. You've got to know bridge abutment X, Y, or Z on bridge 4 of the bypass, whatever it is. So you've got to know where this was. Useless otherwise. No point in testing it if you don't know where it is. So that's basically it. The code of practice for sampling and testing is ISEN 12350 Part 1 is sampling and testing. For those of you who get involved, not something that you probably need to worry about until such time as you take up civil engineering and you're in your concrete laboratory essentially, or practicing. Folks, that's it for here. If you have any questions or queries or want any more information, samples, photographs or whatever, your teacher can go back to us through email or call or whatever you want. There's no problem that way. And on behalf of myself and Owen and Brendan here and the college in general, and James of course, we would like to wish you the very best of good luck with your leaving cert. And when the time comes, if you decide to do a little bit of civil engineering and you decide to do it locally, you have an approximate idea of where we are now and what we're at. So don't forget it. A little bit of political debate there. Okay, folks, the best of good luck.
Just want you just to get a little snapshot